All right, let's dive into a really cool cosmic puzzle. For years, the way we've hunted for planets around other stars is by looking for their tiny little shadows. But what if the stars themselves aren't these perfect, steady light bulbs we thought they were? What if they're covered in spots? Today, we're going to look at a brilliant new technique that actually turns that problem, these stellar polka dots, into an incredibly powerful tool for understanding both the stars and the planets that orbit them. So, here's our roadmap. We'll start with the classic way we find planets. Then we'll get into the big problem that's been making things tricky. After that, we'll look at the clever new solution, why it's such a game changer for finding habitable worlds, and then we'll peek into the future of this amazing tech.
Okay, so first things first. To really get why this new technique is such a big deal, we have to talk about the workhorse method that astronomers have been using for years. It's the foundation for everything. And I mean, this method has been wildly successful. Just look at that number. Thanks to space telescopes like Kepler and TESS, we now know of more than 5,000 planets outside our solar system. 5,000! Think about that. And almost all of them were found using this one technique. It's called the transit method. And the idea behind it is actually pretty simple. You stare at a star, and you wait. If a planet's orbit is lined up just right, from our point of view, it'll pass in front of its star, and when it does, it blocks a tiny bit of light, causing a little dip in the star's brightness. It's kind of like watching a mosquito fly in front of a distant streetlight. What's just incredible is how much we can learn from that tiny little flicker of light. The size of the dip, that tells you how big the planet is. How often the dip happens, that tells you its orbit, which tells you how far it is from its star and how hot it probably is. And get this. By studying the starlight that actually filters through the planet's atmosphere, we can start to figure out what that atmosphere is made of. It's amazing. It all sounds so clean and perfect, right? But science is rarely that simple. This whole method hinges on one big assumption. And, well, that assumption isn't totally true. And this is really the heart of the problem. For the transit method to work perfectly, we have to assume the star is this perfectly smooth, evenly bright ball of light. But what happens when it's not? What happens when the very thing you're trying to measure against is changing all on its own? This really shows you what's going on. On the left, that's the dream, a nice, clean, predictable dip when the planet goes by. But on the right, that's reality. The data we actually get is often messy, it's bumpy, it's full of all these other little dips and wiggles. It's like trying to hear someone whisper your name from across a really loud, crowded room. The planet signal is in there, but man, is it hard to find. So what's making all that noise? Well, they're called star spots. And you're probably already familiar with them because our own sun has them. We call them sunspots. They're just cooler, darker patches on the surface. And since the star is spinning, those spots rotate across its face, causing their own dips in brightness. These are the polka dots that mess everything up. So that leads to the million-dollar question. How do you separate the planet's clean signal from all the noise made by the star spots? For a long time, this has been a huge headache for astronomers. But now, a team of scientists has come up with a really clever model to do exactly that. The lead author of the study, Sabina Sagimbayeva, put it this way. She said their method basically faces the problem head-on. Instead of just trying to ignore the star spots or filter them out as noise, they decided to map them. They turned the problem itself into a solution. So here's the magic trick, broken down into 3 steps. First, you take that messy, bumpy data from the telescope. That's your input. Then, this new model, called starry-starry process, does its thing. It mathematically teases apart the 2 different signals, the one from the planet and all the ones from the rotating spots. And what you get out is just incredible. 2 perfectly clean sets of data. One is the pure, accurate signal of the planet, and the other is an actual map of the star's surface. And this isn't just a theory, they've actually done it. The team tested their model on a real star system about 141 light-years away. And by using this process, they figured out that this particular star has most of its spots clustered around its north pole, which just so happens to be tilted right towards us. So it works. It gives us real, specific details about stars that are incredibly far away. Okay, so mapping star spots is a pretty neat trick. But this is where the story gets really, really exciting, because understanding a star in this much detail has massive implications for understanding its planets, especially when we're talking about the search for life. One of the team members, Brett Morris, said it creates a feedback loop, and that's the perfect way to think about it. The more you learn about the star, the more you learn about the planet. And the more you learn about the planet, well, that tells you more about the star. They're completely connected. So what does this feedback loop actually let us do? For one, by getting rid of all the star's noise, we get a much cleaner, clearer look at the light coming through the planet's atmosphere. We can also figure out the true angle of the planet's orbit, and we get a better sense of how active or stormy the star is, all of which is absolutely critical for figuring out if a planet could support life. But here it is. This is probably the most important example of all. It turns out some cooler types of stars can actually have water vapor in their own atmospheres. So imagine you're looking for that chemical signature of water on a planet. You know, the holy grail for finding life. You have to be absolutely certain that you're not just seeing the water on the star itself. This technique helps us tell the difference, and that helps us avoid a massive false alarm in the search for life. So this is a huge step forward. But, like with any new science, there are still some limits, and there's a really exciting future to look forward to. Right now, the starry process is built for visible light, the kind of stuff that telescopes like Kepler and TESS collected. That means, for now, it can't be used on the infrared data that's pouring in from the James Webb Space Telescope. But that's almost certainly going to change as the model gets even better. You can really see how this fits into the grand story of how we explore the universe. In the past, you had missions like Kepler and TESS, whose whole job was just to gather tons and tons of data. Right now, in the present, we have tools like starry process that let us refine that data and pull out incredible new details. And in the future, we have missions like the Pandora satellite, which is being designed specifically to observe stars in many different colors of light at the same time, which is a perfect setup for this kind of advanced analysis. So we started out thinking of these star spots as a problem, right? Just noise getting in the way. But by taking a closer look, scientists have turned that noise into a key that doesn't just unlock a map of the star, but also gives us a much clearer window onto the worlds orbiting it. And it just makes you wonder, what other secrets are stars hiding in their light, just waiting for us to build the right key to unlock them?